creating exponential functions. And so we've looked at geometric functions, and those are kind of cool because they always follow that pattern. But they're actually exponential functions are geometric functions. So really, we're not going to be taking it that far by creating a geometric exponential function. So in an exponential function, we represent it by f of x, which is equal to a times b of x, which if you remember a geometric function, f of x was equal to f of 1 times the common ratio r to the n minus 1. So this is actually very, very, very similar. And then, of course, a and b are all real numbers, and a does not equal 0. And b is bigger than 0. So let's go ahead, look at an example. An example of this type of function would be really simple, would just be like 2 times 3 would be an exponential function. And the graph, if I were to make just a little quick graph, exponential functions generally are going to kind of do this. Like, remember, if you're thinking about population, it starts out slow and then it starts to increase. And it should be a curve there. But of course, my mouse isn't wonderful. So let's go ahead and do an example. We're just going to calculate the exponential function, calculate the input-output tables given values given the domain, and then graph our function. So if I have the function 3 times 1/2 to the x, then I'm really just doing 3 times 1/2 to the negative 1 power, and with the domain of negative 1, 0, 1, 2, 3, 4, which just means those are the values I'm plugging in for x. So 3 to the 3 times 1/2 to the negative 1 power is 6. Because remember, when you have a negative exponent, it's going to flip it. 3 times 1/2 to the 0 power is 1. Anything to the 0 power is going to be 1. But 3 times 1 is 3. 3 times 1/2 to the 1 power is 3 times 1/2, which is 3 halves. 3 times 1/2 to the 2 power is 3 times 1/4, which is 3/4. And then we have 3 times 1/2 to the 3rd power, which is 1/8. And 3 times 1/8 is going to be 3/8. And as you can see, the denominator is really the only thing that's kind of changing, right? We are always multiplying by 3, so we're always going to have 3 in the numerator. But the denominators, that's the only thing that's actually being affected by that exponent. So 3 to the 4th power is going to be 3 over 16. Because we're just continuing to multiply by 2 each time in the denominator. All right, so now that I got my values, I'm going to go ahead and graph them. So my first point is at negative 1, 6, which is way up here. And then I have a point at 0, 3. And then 1 and 3 halves, which remember is 1 1/2. 2 and 3/4. 3 and 3/8, which is a little bit less than a half. And then 4 and 3/16. So as you can see, I'm getting closer and closer to 0 as I graph my line, to graph the points. And we would expect it to get infinitely close to 0, but never actually reach 0. So this is what the exponential function is. It starts to flatten out at some point. Okay, and that's kind of one of the key qualities of there. So in this next example, now that we've created an exponential function, we're going to take what we know about geometric sequences and we're actually going to write an exponential function. So when folded a piece of paper in half, the total thickness doubles. Suppose an unfolded piece of paper is 0.1 millimeters thick. The total thickness of the paper is an exponential function. Okay, so this is really kind of where we can take what we know about geometric sequences and apply them to create exponential sequences. So remember, geometric sequence was f of 1 times the common ratio to the n minus 1 power. Well, this time we're not starting with f of 1, we're starting with f of 0. So initially, when the page starts, it is 0.1 millimeters thick. So think of it like as the initial value or the y-intercept. If we're thinking about linear equations, then my a value in this case is going to be 0.1. Okay, and then my b value my b value is how much it's increasing in time. And we're being told that it doubles every single time. So my b value is 2. So what's really cool is now that I have my a value and I have my b value, I can make my exponential function. And so my exponential function is just f of x equals a times b to the x. Remember, that's the formula that we're going to be using. So if it's just a times b to the x, then really all I need to write is f of x equals 0.1 times 2 to the x. And I'm done. That is my exponential function. Okay. All right. So we're gonna, now that we've kind of established this, we're gonna go ahead and take it to the next example. We're gonna be writing an equation where we're given 2 points, and it seems pretty daunting at first, but it's actually not that bad. So we have to start by finding b, but if you remember from geometric sequences, b is the common ratio, right? So when we find the common ratio is, oops, this shouldn't be. Okay. The way we find the common ratio is that we set the outputs equal to, we divide the output by the other, right? Remember, because it's just really 12. Anyways, I'll show you. So b is always going to be equal to the outputs divided by each other. So y2 minus y1. So 24 minus divided by 22. Really helps if I put the right numbers in. So 24 divided by 12. I think I said 22. My brain's not working very well, obviously. So 24 divided by 12 is 2. So my common ratio, my b value is going to be 2. That just means that this equation is doubling each time, right? Which makes sense. If I went from 3 to from 12 to 24 over 1 unit, then my common ratio is going to be 2. I'm multiplying by 2, right? And those are y values. So now I need to solve for a, and solving for a is a little bit trickier. So I'm just going to kind of come back to that original formula. F of x, typing this today, f of x is equal to a b to the x. Okay, so remember, that's my formula. So I need to solve for a. Okay, so how I'm going to solve for a is I'm going to take what I know about this problem. So I'm just going to choose a point, and I'm going to choose the point 3, 12. I know b is 2. We just found out that b was 2. I know x is going to be 3, and then my f of x, when I plug in that point, is going to be 12. So when I plug those values in, I'm going to have 12 equals a times 2 to the third power. So what this does is this kind of gives me all the information. I only have the variable a that I need to solve for, which is what I want. So I can just go ahead and solve. Well, 2 to the third power is 8. So I have 12 is equal to 8 times 3. I'm just rearranging, or 8a. I'm just rearranging it because this is something that we're familiar where it's like a, 8. It looks weird. And then remember, to solve for a, I divide by 12. So I end up with that 12 over 8 equals a. And 12 over 8 can be reduced. I can divide both of those by 4. So then a is going to equal to 3 over 4. Sorry, not 3 over 4. Blah. 3 over 2. Okay. So now that I have my a, I have my b, I can go ahead and write my equation. My equation, remember, is just f of x equals a, which is 3/2, which just remember that's how much it started out with, times a, or times b, which is 2 to the x power. And that is my function. So hopefully now you know what a discrete exponential function is. We didn't really go into it, but think about explicit exponential functions and think about how you will represent them.